Today we're going to talk a little bit about trigonometry and how it relates to music, specifically about pitch and tuning. So I have a string instrument, a guitar, and when I vibrate these strings, they produce a note. We can measure what that note is using something like this tuner, and essentially what it's doing is it's measuring the frequency of the sound wave that I produce. So you can see this open A, a little bit flat, has a frequency of 110 hertz. So 110 hertz is our frequency. It tells us how many periods per second that sound wave is going through. So it'll go through 110 periods or 110 cycles per second. We're playing the whole string, which if I measure the length of this string, this is kind of a little baby guitar. So it's right under 2 feet long, 23 and a half inches. So what I can do to play a different note is I can hold down some point on this string. So I'm going to hold right here on the 12th fret, and that's halfway down the guitar. You can see that's right at halfway. When I play that note, we get a high A, which is at 220 hertz. I'll show you the tuner to prove it. So there's the low A at 110 hertz, and the high A at exactly double that, 220. Cool. So the way string instruments works, or at least the way most string instruments work, is we change the length of the string with our fingers or with something else to produce a different note. And so you can see a really mathematical relationship happening here, where by having the length of the string, we're going to look at some other notes in a minute, but we're just relating the A, which is a A2, to this A, which is an A3. You can see that the length of the string is exactly half. Right? I measure from that point I was holding down to the end. That's 12¼ inches. So exactly half of the full length of the string. And we see the frequency doubles. Or we can think of it as if we multiplied by 1/2, we can divide by 1/2. So we have this really tight relationship where by having the string we double the frequency. So we have this direct or inverse relationship. All right, so we can play around with this a little bit more and figure out what would the frequency be for some other notes on our guitar here. So we're going to do the notes of a major triad here. So the next note we're looking at is a C sharp. So that's the third of the A. So from looking at this third, let's measure and see how much of the string are we playing. Again, the whole point with the guitar is I'm holding down this fret here, which essentially kills the rest of the string down here. We're not using it, so we're just vibrating this part of the string. So if we measure that, we get right at 19 inches. So the length of our string to produce a C sharp is 19 inches. So let's see if we can figure out what the frequency is going to be for that with a little bit of math. Actually, let's go ahead and measure for an E as well. So E would be the 7th fret here, which comes out to about 15 3/4 inches. So about 15 3/4 inches. And now I'm not measuring perfectly, so you're going to see our answers are just a little bit off. So that little squiggle means about that much. All right, so let's get our calculator out here. If I'm doing 19 of the 23 and a half inches, what proportion of the string am I using? Let me get this where you can see it. So 19 was the length of the string for a C sharp. So I'm using 0.8 of the string. You see it's not perfectly 0.8. We're a little bit off because of measuring things. But essentially we are multiplying by 0.8 or 4/5. Right? 80% is 4 out of 5. So we should have a frequency of whatever 110 divided by 4/5 is. We maintain that same relationship, that inverse relationship. So 110 divided by 4/5 or 0.8. We get 137.5, and that's pretty much exactly correct. should really be 138.5, but again, our measurements aren't really perfect here. And there's some other stuff going on, but let's try it out. There we go, about 138. So just like we predicted using the length of the string, we produce a sound wave that is proportionally, has a proportionally increased frequency. We can do the same thing with a E. So we have the relationship of being 15.75 out of the 23.5. That's going to be 2/3. So let's just throw that out there. So that's 0.67 or 2/3 the length of our string. So we can do 110 divided by 2/3 or about 0.67. And we'll get 165 hertz. And again, our numbers are a little bit off, but we're really close to that. So let's check it out on the tuner and see if an E is 165 hertz. Pretty good. Cool. So what I want to do next is think about how these notes work together. So when you play a and a C sharp together, for an example, you get a nice harmony, right? The first and the third. So let's think about how that harmony plays out on the graph. All right, so again, I said that when we measure in hertz, we measure the frequency of a note, we're describing how many periods does that note go through per second. So when we see 110 on the tuner, that means we have 110 periods per second. So you can see on this graph, I've got it super zoomed in because on the x-axis here, I've got time. So if I were to zoom out where we can see a full second, okay, so from 0 to 1 second, we would have 110 periods, 110 cycles of this sine wave. So we're going to really zoom in so we can analyze these waves. All right, so you can see I've got an equation here to describe what's going on. Basically, this 360 is converting from degrees to seconds. We want however many times per second. And then we have 110 as our frequency. So 110 cycles per second is what's happening here. So this is the wavelength for that low A note that we were starting out with. Let's look and see what it would be for an E. So the E was 165 hertz. And then we're going to keep the rest of this the same. Does not like that. E, remember E is a number. Let's change these to capital letters. Okay, so remember A of t, E of t, just the name of our function, really inconsequential to what we're looking at. All right, and don't worry about this value right now. We'll talk about it in a second. So this is what it looks like when we look at those two notes together. So we have an A and an E here. So those two notes, A and the E. You notice they sound pretty good together. It's a nice harmony. It's the perfect fifth. And we can actually predict those harmonies by taking a look at the sine waves. So the A is this black guy here. We can see that sometimes it really agrees with the green function. Other times it seems to totally disagree. Right? We have this green function's at its maximum, while the black function's at its minimum. But although they don't always agree, they do have some nice relationships going on here. So if we take a look at sort of one sort of unit of time here, so I've kind of marked this off with a little spot, we're going to see those exact same ratios that we saw when we calculated this out. We said that to get from an A to an E, it was 2/3 the length. So let's take a look at what's happening in this little interval. Our A note goes through 1, 2, 3, 4 cycles. The E goes through 1, 2, 3, 4, 5, 6 cycles. So 6 compared to 4 is 3/2, right? So we have that relationship, that 3/2 relationship, or as we had it the other way around, 2/3 to get from here to here. So 165 compared to 110, It's going to be 3 over 2, right? 1.5. So that ratio describes how many, basically how many cycle, or how many periods per time unit that these waves have. We can also represent what happens when we put these waves together. And that's pretty easy to do, actually. If I wanted to add these two functions together, think about what would the sound wave look like when we played the two notes together. We get something like, let me change my color here. We get something like this. So this is what it looks like to play a note and its perfect fifth together. So when we play two notes together, we're essentially adding those sound waves together and we produce a totally new wave. And the math is really simple. We just add those two things together. But if we look deep at what's happening here, it's really, really interesting. So there are times where these waves work together. You can see that right here and over here where we drew this line, those waves are in agreement, right? They're kind of in sync right here. So when we look at them added together, we're going to see that at those 2 points, again, where we drew the line and at 0, our wave is amplified. It's taller than it usually is, right? It's being increased because the waves are working together. That's called constructive interference. And there are also times where they disagree. So like right here, you can see that they're almost opposites, the two waves, right? This one's at a maximum, this one's at a minimum. If we look at the combination of these, we see destructive interference. We see that the wave is being, they're kind of fighting each other, right? So we have a smaller amplitude. So this is a really cool idea behind harmonies, and we can see why something like this works. There's a really nice pattern to it, even if the two waves don't totally agree with each other, that we do have these moments where they come together. A really cool example of this is when we tune an instrument. So our goal when we tune an instrument is to get all of our strings to an agreement at the same frequency. So when we play these two notes, they should sound the same, but sometimes, let's loosen one of these up here, we'll hear that they're not really in agreement. So you can hear those beats. You can hear the difference in the wave. I'm hoping that comes through pretty good through the mic. But you can hear those beats slow down. So when a musician is tuning by ear, they're listening to the agreement between those two notes. She does not like that. And you can wait for those beats to slow down. So to get a really good example of this, let's produce two tones electronically that are perfectly out of sync. So what you're hearing is a 440 hertz tone versus a 441 hertz tone. So these two notes are nearly the same, but they're a little bit off, and you can hear it. They feel out of sync. So in fact, they're off by exactly one period or one cycle per second, right? We said hertz was how many periods per second. So those beats we're hearing are actually marking out exact seconds. I can prove that by tapping out what I hear on this metronome. And we get exactly 60 beats per minute, or exactly 60 seconds per minute. So the difference we can hear that one beat difference per second, that one cycle difference per second. So when a musician is tuning their instrument, they're listening to those beats and slowing them down until we find that frequency that aligns with the other note. To look at this further, we can go back to the graph and take a look at what 440 hertz and 441 hertz would look like together. And you can't even see the difference. Again, it's very slight. You can't even see that there are two functions there unless you really, really, really zoom in. You can see there's actually two lines. But if we combine those two functions, so if we combine those two notes, we're going to be able to see that interference really clearly. So let's zoom out here. What we're seeing is we have these 1 second cycles. So you can see we're at sort of the maximum of this wave here, right? We have the thickest part of the wave. 1 second later, we're back at the thickest part. So you can see those beats that we're hearing when we play these notes together. Sorry, I think that was very loud. This is what we're hearing. We're hearing those fluctuations per second. So I hope you all got something out of this lesson. I think it's really interesting to study music from this perspective, to think about it mathematically, about what makes a perfect fifth sound so nice versus a tritone, which sounds a little off. And I think it has a lot to do with these ratios, about thinking about how the cycles of those sine waves work together. I think it's also really interesting to think about this culturally, how it might sound really good to our ears, but a different culture might not hear it that way, which is also really interesting. So that's not something we can ignore either. For example, Indian music has more notes. There are notes that don't really line up with anything we use in Western music, and it's really interesting. We get some really cool perspectives by studying music that's come from other places. Anyway, I could talk all day about this stuff. To complete your async assignment, just answer the question after the video. Thanks, guys.